Hi, and welcome to Unit 57. In this unit we're going to talk specifically about some kind of a stars, namely the binary system of stars. And this is usually when you have two stars next to one another. So they orbit one another, so they are gravitationally bound to one another, okay? So that's what that means, okay? So we're going to list the kind of classes of binary stars, and then we're going to calculate the mass, the combined mass of the binary star system using Kepler's third law. And then once we can find basically the center, the barycenter, the center of mass of these two stars, we can actually determine their own masses, okay? So there are three kinds of binary star systems. There are the ones that are visually, you can see actually the star, excuse me, moving, at least in an arc, and the other one moving in an arc correspondingly, and they're close to one another. So this is called the visual binary system. There are another kind of a binary star system where you have the spectrum of one and the spectrum of the other interact with one another, okay? They blur one another. So this is actually a spectroscopic binary. And then you have another one where we are edge on, meaning the Earth is here, the Sun-Earth system that is, and the other star system is on here. So basically what you see one going behind one star going behind the other star and then coming in front of it, okay? Or vice versa, okay? So in this case, we have an eclipsing binary system. So those are the three types of binary systems. Basically, the Doppler effect is a very, very powerful technique in this case, especially when they are edge on, to try to determine a lot of information about them. For those sitting in an astronomy lab, this is one of actually the activities we do, and that is by observing actually not a binary system. We have a massive planet versus a star, relatively average-sized star, and then it goes around it. As it does, the star itself is actually moving, and you look at its spectrum. So, think about it this way. We are here. This is Earth, okay? The sun system. Earth is where we observe the star systems. So the star is at some point moving away from us. So its spectrum, the entire spectrum shifts toward the red because it's moving away from us. And other times it's coming towards us. So when it's coming towards us, the entire spectrum shifts toward the blue. So it's not that the entire spectrum becomes blue color. It's shifted toward the blue. It moves toward the blue, okay? And the shift itself, the amount of shift, determines the speed with which this one is moving, number one, and how often this goes back and forth, basically. At times it's moving away, at times it's moving towards. And then based on that, we're going to determine the period, okay? So a lot of information we can infer from that. In addition to the speed with which it rotates, we can actually find the distance, namely the semi-major axis. So that's a lot of information. So imagine we're looking at the Alpha Centauri system, which made up of two stars, basically, three stars. The one that is Proxima is kind of far from the other two. So you have Alpha Centauri A and Alpha Centauri B. Here is A, here is B, and they orbit one another. So B is this kind of orangey color, and the A is the yellow one. So now, as they orbit one another, you're going to determine their period using the Doppler effect if you want to, or the direct observations, because this is actually a relatively close by system. So it's about 4 light years from Earth. So at this point, you're going to determine the period. How often does it go back and forth, okay? You don't really have to wait 80 years. So this system takes about 80 years to go full cycle around, back to where it started from. As long as you can determine the arc and you determine the period it takes that arc, you can extrapolate to 360 degrees. That's one thing. The other thing also is to determine, again, how the semi-major axis. Now, using Kepler's third law, you have basically the sum of the two masses, MA and MB, okay? They are about 2 solar masses. If you use this formula, you have basically 23 cubed divided by 80 squared is 1.9 solar masses. This formula basically is in terms of solar masses. So if the sun mass is 1, this formula will be 1 equals to a cubed divided by p squared, okay? Or p squared is equal to a cubed. But that's if it's one solar mass, but this one is actually not one, it's 1.9. So that means that this is almost 2 times the solar the mass. So basically, there's two stars there about twice the mass of the sun, slightly less than twice. Okay, that's not enough though to determine the mass of each star. So you need to at least find this A. Once you find this A, then you can go back and find or at least you have to, because this gives you the sum of the two masses. But if you have somehow the ratio of these two masses, then it becomes a matter of algebra trying to find the individual masses. This is exactly what we do in this case if we know the center of mass, the point with which both stars are orbiting. Okay. So this one is, let's say, this distance from that very center, and this one is this distance from that very center, and using the relationship that we know for the very center. So if we know the distance from star A to the very center, and the distance from star B to the very center, the ratio of these two distances is the same ratio of the two masses, or the inverse of the two masses. Now you have two equations. So if you took any algebra classes at all, it's very easy to solve a system with two equations with two unknowns. Okay, so that's basically the way to find the masses. So now you gain a lot of information about this star system. So we're trying to build a ladder from this point on. Once we determine properties of the stars, we're going to extrapolate them and find all kinds of information about them, so that you know one of these two stars is slightly more massive than the sun. I'm going back to the Alpha Centauri system. One of them is slightly more massive than the sun, and the other one is slightly less massive than the sun, and they're both roughly the same size of the sun. So the point being in here is binary star systems are very, very common. They represent about 50% of the stars out there. Once we gather enough information about them, we can extrapolate and have a vision or an image of how everything looks like in terms of the other stars. Thank you.